All right, let's go ahead and get started. Thank you so much for joining today and welcome to today's webinar called Standards for Measuring the Impact of Extreme Weather Event Exposures on Health, Challenges and Considerations. My name is Ashlyn Quinn and I am a program officer at the National Institute of Environmental Health Sciences. I'd like to introduce our two speakers, Kacey Ernst and Melissa Furlong. Dr. Kacey Ernst is professor and chair of the Department of Epidemiology and Biostatistics at the University of Arizona Mel and Enid Zuckerman College of Public Health, where she has been a faculty member since 2008. Her research focuses on the environmental and social drivers of infectious diseases, particularly vector-borne diseases such as malaria, dengue, and Zika. She has led field-based studies in Kenya, Indonesia, Mexico, and the southwestern United States, examining mosquito ecology, transmission dynamics, and public health interventions. Kacey serves as one of the co-MPIs of the SCORCH NIH-funded P20 Exploratory Research Center, focused on building research and workforce capacity to address the health impacts of extreme heat in the US Southwest. Dr. Melissa Furlong is an environmental epidemiologist who studies the chronic health effects of environmental contaminants with an emphasis on pesticides and neurological outcomes. She holds a PhD in epidemiology from the University of North Carolina at Chapel Hill, a master's in public policy from Duke University, and a BS in psychology and neuroscience, also from Duke University. She is the recipient of a Pathway to Independence Award from NIEHS, a K99R00. Dr. Furlong's primary research interests include developing and implementing novel approaches in big data to investigate associations between environmental contaminants and longitudinal chronic health outcomes, particularly neurological health. And she is also involved in the SCORCH Center as the lead of a research project on the health impacts of heat waves during pregnancy. So thank you both for being with us today, and I will hand it over to both of you to start your presentation. Thanks so much for being here.
Wonderful. Thank you so much for that introduction. And so today we're going to talk a little bit about some work that we've been doing here. Great. So I'm Kacey Ernst, and this is Melissa Furlong. So we're going to trade off sort of halfway through the webinar today. So we're going to talk about some work that sort of I started thinking about this several years ago when my lab was conducting a review on flooding and mosquito-borne diseases. During that process, we noted that the heterogeneity in how extreme weather exposures were defined and measured was really pretty significant. And then in subsequent discussions with colleagues, I've sort of expanded that work into extreme heat, and it's also just become really clear that this is a common issue across extreme weather and health research. So we have several objectives for today. First, we want to talk about some of the common challenges in measuring extreme weather exposures in epi studies. And I'm going to frame this with lessons learned from that review that we conducted where we were associating flooding and mosquito-borne diseases. Then Dr. Furlong will walk through a really nice case study where she simulates how choices for defining extreme heat actually impact the identified relationships with pregnancy outcomes. And then finally, we'll wrap up with some initial thoughts on what can we do as a research community to further the discussions around developing standard approaches for quantifying extreme weather exposure. All right, so one of the first challenges that we face is that extreme weather is not really a single universally defined construct. In general, it's broadly defined as a meteorological condition that exceeds some historical threshold. But that cutoff can be really subjective. Some researchers use absolute thresholds, some use percentiles, standard deviations, or event-based classifications. And so, as you'll find from Dr. Furlong's case study, that can make a really significant difference. So one of the other sort of issues is that the meteorological event itself is often actually quite distally related from the biological processes that are directly influencing the health outcome. So between the meteorological hazard and the outcome are a series of mediating mechanisms. So environmental changes through infrastructure disruptions to the natural built environment, socioeconomic disruptions, to all the way to resulting health-related exposures that directly impact the physiology and that health outcome. So, for example, extreme rainfall, which I study, may lead to flooding, which then alters housing conditions, increases vector breeding habitat, displacement patterns are also altered. And all of that can sort of modify vector densities and vector human contact. However, at the same time, the exposure to the hazard, as well as the impact of that exposure on the actual health outcome, are modified by social and structural factors that are already in place. Things like housing quality, baseline health status, resource infrastructure, all collectively determine if a high rainfall event in one area will actually lead to mosquito-borne disease changes, which may not be the same in other locations. So weather events are also not occurring in isolation, and broader weather patterns have to be considered. So for example, flooding after drought is often connected with higher levels of West Nile virus transmission. Okay, so this sort of begs the question, so how do researchers actually decide which exposures should be measured across this pathway? So do we measure the meteorological event itself, the environmental changes and disruptions, the personal exposure, the biological responses? So the answer really depends not only on the research question and our current understanding of the causal pathway, but very often it moves from what we should measure to what we actually can measure based upon the availability of the meteorological and health outcome data. All right, so some of those choices are going to be limited by technical, spatial temporal, conceptual, and structural challenges. So from a technical perspective, investigators are often working with very different underlying data sources. Some studies actually rely on weather station observations, while others are using satellite products, gridded climate models, reanalysis data sets, or administrative disaster databases. And each one of these data sources has its own strengths and weaknesses. It is measured at its own spatial scale, temporal scale, and there's different uncertainties and assumptions that are made. So for example, if you're looking spatially at spatial heterogeneity, exposure could be assigned at a household level, a neighborhood level, a regional level, and each one of those scales is going to capture different processes while introducing different forms of exposure misclassification. Temporally, hourly data versus monthly data is going to also relate to very different biological processes. So then even when investigators are attempting to measure the same phenomenon, such as flooding or extreme heat, the resulting exposure metrics may actually differ relatively substantially and depend upon the actual context in which that data is being collected. So going to that case study that I was talking about related to flooding and mosquito-borne diseases, the complexity really starts to show up when you're trying to harmonize and get a sense of a general question, and you start looking across research studies. So it seems like something like heavy precipitation and flooding should just lead to more water, more habitat, more mosquitoes, and more disease. But like with most things, the picture is pretty complicated. And as you see in this summary of findings for malaria and dengue, the message is mixed. There seems to be an important temporal lag. 1 to 4 months post-flooding has the strongest sort of consistency of increased association for dengue and malaria across studies, but it isn't ubiquitous. Some studies found no effect and others found a reduction in disease. So the question is, are those differences among these studies due to genuine differences in the mediators of the causal pathway? So for example, are some locations just more prepared to have surveillance and control strategies in place post an event? Or are there differences to exposure definitions, lag structures, spatial scales, and the mechanisms that are actually being captured? So when we dug into the literature to identify how different studies actually defined sort of this extreme precipitation and or flooding, we found a lot of significant heterogeneity. Some studies actually defined flooding using rainfall threshold, so that meteorological side, with percentiles or anomalies. And then others used event-based definitions, so a named disaster, a named flood. And some measured the actual inundation of water over the land. So they used satellite imagery to see what proportion of the land was inundated. They used river gauge heights, or they used self-reports of standing water in a community. So each one of those is going to actually capture something slightly different, even though the overall concept is similar. So rainfall is presenting the meteorological event. Inundation may reflect direct human exposure, and event-based definitions may actually capture social disruption more than hydrology. So the choices of exposure actually really matter, as you'll see in just a minute. Even small changes, such as a shift from the 95th to the 99th percentile, could represent different levels of biological stress. Percentile thresholds do improve our ability to compare statistically, but they may actually reduce the biological comparability across studies. Things like temporal scale can change what process is being captured. Daily exposure is going to reflect the acute physiological effect, while monthly or seasonal measures may capture ecological or infrastructure related impact. Binary definitions are going to be a lot more simple to interpret, but they also lose some important dose response information that a continuous exposure measure or leveled exposure measure may preserve. And then spatial scale is also going to matter. As I mentioned before, individual exposure misclassification typically increases as you aggregate from household to a community or a national level. And then the measures that are being, the mechanism that's being measured is really critical. So rainfall isn't the same as flooding. Ambient temperature is not the same as personal heat exposure. So measures that are more proximal to the biologically relevant exposure pathway may support stronger causal inference. So these exposure decisions are not just technical choices. They reflect assumptions about the underlying biology, mechanisms, and causal structure connecting extreme weather to health. So this is the causal web that we put together in our review paper for the flooding and precipitation and the mosquito-borne diseases. But a lot of times what happens in this research is that we move from sort of this complexity. It's really difficult to measure all of these components in a single study. And so we might end up succumbing to this epidemiological black box. If you're only using those distal exposure measurements and then connecting them to health outcomes like dengue or malaria transmission. And so it's really important to understand those things that are going on underneath that box to develop effective interventions, or to even know which communities might be at risk for challenging health outcomes after an event. Okay, so I'm going to go ahead and turn it over to Dr. Furlong to talk about an example which seems like it could be a little bit more straightforward, which is exposure to extreme heat during pregnancy and its impact on perinatal health. It seems like it could be more direct. You have that meteorological variable heat as the actual quantifiable exposure directly affecting the physiology of the woman and her fetus. So I'll let her go ahead and talk about a simulation experiment that she conducted to look at different definitions.
Okay, so let me just give everybody a little bit of context before we dive into this very sort of specific technical series of problems that we go through. Okay, so epidemiological models of the associations between heat exposures and health outcomes have been becoming a lot more common, especially over the last 5 to 10 years. And as Kacey mentioned, okay, so these associations are becoming more common. And as Kacey mentioned, we have some challenges with heat that we haven't necessarily had with some other environmental exposures. So heat is extremely geographically diverse across the United States, but also across most geographical scales that we're looking at. And I think when a lot of us started this research, we thought it would be pretty similar to air pollution. And there are some similarities to air pollution, but there's also some critical differences. So air pollution is pretty tightly regulated, so we don't see huge differences from region to region beyond sort of the standard EPA caps. But heat is completely unregulated, right? So temperatures that are experienced in Miami or South Texas or in Arizona might never be experienced in Montana or North Dakota or Maine. But when we're linking these huge data sets across national models of temperature with national health outcomes data, or even state-based health outcomes and state temperature data, we're going to have a lot of variation in our exposure by geography. So as we were doing our research project where we're modeling heat waves during preconception and pregnancy and looking at associations with neurodevelopmental indicators in childhood, we were coming across a lot of these challenges. And there were a lot of modeling choices that Kacey mentioned in the first half of the presentation. And we wanted to know sort of what were the trade-offs of some of these different heat models and the different modeling choices from an epidemiological perspective. So biologically, we're modeling heat exposure during pregnancy. And I just want to give just a really quick overview of sort of what's happening as we progress through these heat exposure stages. So in stage 1, we have just regular heat exposure, which might not have sort of any health effects, right? So the body might cope comfortably, you might have behavioral avoidance, seeking shade or seeking rest. And then we progress into heat stress, where we have a little bit more active thermoregulation by the body. Might experience some blood diversion. And then we progress into heat strain, where we start to get a little bit more worried about possible heat effects. And then the final stage is heat illness, where we're going to require treatment and hospitalization. So this is personal heat. These are all personal heat measures, which if you think back to the DAG, that's what that is. And then these are health effects, right? So what the underlying biological model is looking at personal heat and health effects, but what we're looking at when we have these national models is really ambient heat. So if we look at the sort of simplified DAG, right, we have ambient heat, maybe some heat adaptation, personal heat, and health outcomes, and then a variety of other variables that are mostly in here, although some can also come out here. So some of the modeling choices that one has to make as they're doing these epidemiological models of heat exposures is they have to start with how we're going to deal with ambient temperature exposure modeling. So first we have to choose, are we going to do absolute temperatures or relative temperatures? So when we're defining heat waves, are we going to use a threshold of 100 degrees, or are we going to use a threshold of the 95th percentile? Are we going to correct for humidity? When we think about heat waves, should we be using 3-day heat waves, 4-day heat waves, 5-day heat waves? What are the different thresholds that we need to be using? For instance, 95th or 99th percentile, or for absolute temperatures, what's the threshold we need to be using? Should we be looking at average temperatures during the day, peak temperatures, minimum temperatures? Should we be considering daytime or nighttime temperatures? And then there are a ton of different models for temperatures that incorporate a variety of different geographic, satellite, and ground-based measures. And then there are the sort of standard questions that we might ask for most environmental models during pregnancy. So what kind of statistical model should we use? Should we use distributed lag modeling versus other? There are many advantages to DLMs, but also some disadvantages. Should we adjust for location in data with heterogeneous locations? And then if we're looking at pregnancy and we have different gestational lengths for various prenatal outcomes, do we need to account for those? If we're doing a DLM, do we need to account for those the cross bases that don't have a complete exposure matrix? And so we have to account for that with risk set modeling. And then we have, the standard, do we do a binary outcome or a continuous outcome? And then for sensitive windows, if we're looking at preconception, which we would have the opportunity to do in these types of models, how far back do we go? And then are we going to look at trimesters, or should we look at weeks? And then for acute events, we have to consider, are we doing the day before, the week before, the years before? So this is just a summary of some of the choices that we have to make. But in this simulation, we're only going to focus on a couple of things. So we're going to look at absolute versus relative temperatures, so thresholds of 100 degrees versus 95th, the actual cutoffs for those thresholds, and then adjusting for location, and then also looking at heterogeneous locations. So we ran a simulation to test all of this. And then when you run a simulation, you have to choose some underlying biological truth that you're comparing everything against. Okay, before we get to that though, we'll do just a brief overview of what I mean when I say absolute versus relative temperatures for defining heat waves, so that everybody's on the same page, because this is sort of the crux of the simulation. So when I say an absolute threshold, we're talking about, for instance, 100 degrees Fahrenheit. It doesn't necessarily need to be 100 degrees Fahrenheit, but here, any day above 100 degrees Fahrenheit contributes to a heat wave definition. And here, a heat wave definition is going to be multiple days in a row where the max temperature is above 100 degrees Fahrenheit, regardless of the location. And there are a couple of advantages to this in that it might reflect a true human temperature threshold for heat strain or heat sensitivity. And you can make the argument that a human body core temperature is pretty consistent across locations. Humans require certain body temperatures to function, and also there are fairly rigorous cutoffs for things like fever or for when your body's actually entering into heat strain, right? It's not like everybody has a different threshold for heat strain. Everybody has the same personal body core threshold for heat strain. So there's that argument that the absolute temperature might reflect an underlying biological reality. The disadvantage is that some cities might have zero heat waves, right? So South Texas, Miami, Arizona is going to have a lot of heat waves, but up here in the northern continental United States, you're probably going to get very few if you use some of these cutoffs. And some cities, and if you're trying to balance it, then some cities might be just one long constant heat wave. So to combat that, I think a lot of people have adopted this concept of percentile thresholds. And this comes out of a very long history of using just standardized measures for comparability purposes. So basically here we take all of the daily max temperatures across a given city across the last year, the last 5 years. We identify the top 5 percentile or the top 1 percentile, and we cut it off and we say, okay, a heat wave is anything above that 95th percentile or 99th percentile. So here, for instance, in Phoenix, your 95th percentile cutoff might be 110 degrees Fahrenheit. And in Seattle, a 95th percentile cutoff might be 80 degrees Fahrenheit. The advantages here is that you get better distribution of exposures across cities, including cool cities. So you're going to have people who are exposed to high heat days, no matter where you are. It's more helpful from a modeling perspective. And then it might also reflect human adaptation to extreme heat. The disadvantages are that in a particularly temperate area, a heat wave might be up to 3 days in a row at 75 degrees Fahrenheit, which might not accurately reflect heat strain or heat stress. Okay, so for the simulation, we had to model the biological truth. And so this is just sort of one possibility. We're not necessarily saying that this is absolutely the biological truth. This is just how we modeled it in this particular example. So we assumed that below some temperature, sorry, the x-axis here is temperature. Below some temperature, there's no increasing risk for an adverse outcome with each increasing degree, right? So you can imagine that going from 30 degrees Fahrenheit to 31 degrees Fahrenheit does not increase your risk of a heat-related illness at all. But above some temperature, there probably is some linearly increasing risk, right? Like, so going from 105 degrees to 106 degrees to 107 degrees probably does result in some linear threshold. And so we picked 85 degrees Fahrenheit here as the point where risk starts to linearly increase. So this is the true simulated biological model for the simulation. And it was based on the average daily maxes in a given week of pregnancy. So for this simulation, we just looked at 1 week of pregnancy. We just looked at the 20th week of pregnancy. And for all models, we assumed, and we modeled that the risk increases with each degree above 85 degrees, and the odds ratio modeled is 1.005 for each degree. So for all models, we had a sample size of 500,000 births, calculated the odds ratios. We assumed the births were distributed evenly across the calendar year, and we had 100 simulations per combination of cool city type, which I'll talk about in a second. We looked at continuous measures of exposure. So we looked at the number of heat degrees beyond 85, which matches the biological the simulated biological truth. We looked at the number of percentiles past the 85th percentile. We checked a few different absolute thresholds: 85 degrees Fahrenheit, 100 degrees, and 105 degrees. We checked some of the binary percentile thresholds, so 95th and 99th percentile. We looked at what happens when we adjusted for city. And then we looked at what happens across various makeups of different types of cities. So we considered 2 cities, so cool cities and hot cities. We assumed that our sample of 500,000 people came equally from 10 different cities. And we looked at what happened when we had all hot cities and then going up to all cool cities. So 0 cool cities is all hot cities, and 10 cool cities is all cool cities. These are the temperature distributions just as the cool cities increase. So this is from the simulation. So here, this is the temperature distribution in 0 cool cities, which is all hot cities. And then down here is the temperature distribution for all cool cities. And you can see that we have a decent amount of exposure above the 105-degree cutoff or the 100-degree cutoff. Up here in hot cities, the numbers of people exposed goes down as your cool cities increase, right? So down here, we have very few people who are actually exposed when we're at 10 cool cities. This is the absolute threshold cutoff. You can also see when you just when we split it out by hot and cool cities, we can see that all of the exposed are driven by hot cities, regardless of the cool versus hot makeup. For the percentiles, these are percentiles. Each one is a city-specific percentile cutoff. You can see you have a decent number of exposed people across hot cities, and you have a decent number of exposed people across the cool cities. But the thing to note here is that your absolute threshold cutoff for cool cities and hot cities are really far apart, right? So depending on your model, you have a very large degree of people who are who have their exposure misclassified in here. All right, so let's start with the simplest to interpret exposure model. So we're going to start by looking at what happens when we model our exposures, our simulated exposures as being at above the binary absolute threshold of 100 degrees Fahrenheit and the binary percentile threshold above the 95th percentile. So the way to think about this is imagine a gestational week 20, and if a participant is exposed to a temperature over 100 degrees Fahrenheit for three days in a row, they get a 1. If they're not exposed for at least 3 days in a row, they get a 0. And over here, it's the same thing, except it's the 95th percentile for 3 days in a row. Okay, so here we have, this is the 100-degree threshold, and this is the 95th percentile threshold. And the way to interpret these plots is here we have number of cool cities across the x-axis. So here we have all hot cities, and here we have all cool cities. The y-axis is the estimated odds ratio. The dark red line is the true odds ratio, and these lines are the modeled odds ratio. So, and blue is unadjusted and red is adjusted for city. So here you can see with the 100-degree threshold, we generally underperform the true effect until you get up here, but it's not that bad. It's not super far off. You can see that adjusting for city kind of pushes you closer to the null, so it's not ideal in this situation, but in general, this model isn't terrible. Over here, the thing to note about the 95th percentile threshold is that the true estimated effect actually changes dramatically across the type of city, right? So, and this is because at 0 cool cities, the 95th percentile is going to be close to 105 degrees. So the effect is going to be extremely exaggerated. But at 0 cool cities, the 95th percentile is going to be something like 80 degrees or 81 degrees. And because in the biological truth, we set the effect to happen at 85 degrees, there's going to be no effect at that 95th percentile. So the irony here is that under this sort of assumed biological truth, even though we like to use percentiles so that we can get good exposure distribution when we have a lot of cool cities, the true effect estimate is actually going to be really close to the null as you get more cool cities. The other thing to note is the percentiles generally underperform. Adjusting for city does not help with this underperformance, and the simulation intervals, which are kind of like the confidence intervals, are really wide here, right? So here you would see no effect at all. There's just, if you use the percentiles under this model, you're not going to see a significant effect. Okay, so just expanding on that model, if we look at the different thresholds, so 85 degrees, 100 degrees, 105 degrees, and then I think we also use the 85th percentile, 95th, and 99th. Just really quickly, when you use the 99th percentile, the simulation interval is so wide, it's really hard to see what's going on. So I just excluded that confidence interval or that simulation interval. So here you can see that there's a dotted red line, which is the true effect for each threshold. So the red is the 85 degrees. The brown is 100 degrees, and the green is 105 degrees. And generally, you can see that these all sort of give you fairly similar effect estimates, but generally underperform. But the 100 degrees and the 105 degrees really underperform their true effects, whereas the 85-degree cutoff is almost exactly on the mark, even up until you get to around 10 cool cities. These are inestimable at 10 cool cities. For percentiles, 95th and 85th generally give you, again, similar effect estimates, but the 95th percentile is farther away from its true estimate than the 85th percentile. And again, the confidence intervals here are a lot wider, and you can see again that this drift towards the null as your number of cool cities increases. Okay, so then just for comparison, we looked at a continuous measure of exposure where we were just modeling it basically the same way that we had modeled the biological truth, where we had just number of degrees past 85 degrees, right? So if the average weekly temperature for gestational week 20 was 90 degrees, then that person got a 5. If it was 91 degrees, they got a 6. And then the same thing for percentiles, except it was past the 85th percentile. And what you can see here is that the when you model it that way, your true effect and your estimated effect are almost exactly the same. And then for the percentile excess, again, you see this dramatic decrease as you get closer to more cool cities. And the confidence intervals again are tighter, or sorry, the simulation intervals again are tighter for the absolute temperatures compared to percentile. So this has some implications in that, let me go back to the first one. The implications for this true effect are that if you're going to do a meta-analysis and you're comparing the effect of the 99th percentile, the true effect of your 90 or your 95th percentile, the true effect of your 95th percentile is going to vary dramatically depending on the makeup of the types of cities that are included in your study. So the generalizability is going to be very poor for comparing across studies. Okay, let's go back. There's a little bit of a delay here, sorry. Okay, so some of the conclusions here are when we do the continuous measure of exposure, the absolute measures are consistent across the heterogeneous city makeup and tend to be less biased. For the binary absolute thresholds, 85 degrees seems to outperform 105 and 100 degrees on average for bias. And this is just because 85 degrees is the accurate sort of cutoff for exposure misclassification. So when you use 100 degrees as your cutoff, you're inaccurately misclassifying everybody from 85 to 100 degrees as unexposed when really they were exposed and there is a true biological effect there. And then for the percentiles were pretty biased with really wide confidence intervals, but the 85th did outperform the 95th and 99th in terms of bias. We did not observe any importance for adjusting for city in this model, but we also explicitly did not include a link between city and the outcome in our underlying truth model. So you'd have to consider that in a more real world situation. And then for climate heterogeneity, the mixture of cool cities can dramatically affect the estimates under certain modeling assumptions. Okay, so under these conditions, the takeaway is basically try to use absolute measures and not percentiles. Of course, the true biological model is unknown, right? We don't actually know that yet. We haven't looked more at heat wavelengths. There's a little bit more DAG work that we need to do on the percentiles, and then a lot more methodological work that still needs to be done just in general for modeling heat. Okay, back to Kacey.
Okay, so thank you, Melissa, for that. That was not quite as simple and straightforward as we would have liked it to be, but I think that's why we were having this conversation today, or we want to sort of have this conversation today, is to really start thinking about, okay, where do we go from here? Because of these complexities, because of these nuances and how you choose exposures, et cetera, impacting those results that we find, and wanting to be able to sort of get some general principles and understanding of, okay, how does heat affect pregnancy outcomes? We need to sort of make this movement towards having conversations around standards and strategies to ensure that we can harmonize our findings across research studies. So when I sort of started thinking about this, it sort of feels like we need a layered approach, like most things. Trying to have both approaches that an individual investigator or research team can actually commit to doing, having cross-institutional collaborations, and then, of course, at that higher level, having cross-agency and cross-professional society. So that's professional societies, not big society. Having conversations and really starting to just think through how do we create standards, incorporating information from multidisciplinary approaches. It's really critical that we bring in our climate science folks. They know a lot more about the measurement and data collection processes for those meteorological variables. And there are a lot of uncertainties and issues with even just capturing what the temperature is that would need to be incorporated into our lens as well. And then also throughout sort of all the layers, ensuring that we have better data access and quality improvement for everyone. And so one of the, I think the fortunate things is that a lot of these conversations are starting to happen, particularly in the extreme heat community. There is discussion about how do we improve our measurement of extreme heat? How do we make it more related to actual individual exposure, et cetera? So just a few sort of thoughts to sort of kick off the conversation. From the investigator level, I think one of the most important needs is to actually have greater transparency and consistency in how we report our exposure decisions. So how did you decide to use this specific definition of heat waves? How did you decide to use this specific definition for extreme precipitation? And then really clearly describing the spatial and temporal resolution of those exposures, the lag structures that you included, the threshold definitions, and why those choices are aligning with your research question and/or data availability. We also need to ensure that people are conducting sensitivity analyses. So compare alternative exposure definitions rather than just presenting one sort of single exposure definition and going with that as definitive. Making sure that there, as much as possible, is inclusion of that broader context of concurrent and meteorological driven hazards. That'll really start to refine our understanding of how these meteorological hazards interact. So drought followed by flood, extreme heat followed by wildfires. So all of those things are going to create even more sort of unique situations that need to be investigated so we can tailor our understanding to a specific situation. And whenever possible, trying to validate whether things like these ambient proxies are actually capturing meaningful individual level exposures through the use of wearable devices or refined modeling approaches. And then capturing intermediate factors along the causal pathway where feasible. Whenever you can, try to include those potential effect modifiers or confounders in those association studies so that we can move our understanding forward. So one of the things that I think is really important also is to understand how do we meaningfully capture real individual exposure. And there has been significant progress in the extreme heat community on that. But it's important to understand where in this process from meteorological exposure to health outcome that the real impact is occurring, because that's how we're going to be able to determine and identify where we intervene. So what are we actually going to do to interrupt this pathway of weather impacts on health outcomes? Okay, so at that institutional level, so bringing together people from multiple research teams together, what can we actually do? I think there's a really major opportunity for collaborative standards development, standards that are flexible to the research question, the availability of data, as well as the discipline. There's not going to be a one size fits all, right? We've already talked about how different geographic areas have different accessibility to data sources, et cetera. It's really critically important to ensure that we're flexible in those standards. But having benchmark data sets that allow investigators to compare how different exposure definitions perform across settings and outcomes, enhancing multi-site validation, and where the data quality is high, that can really allow comparisons between observational and modeled exposure data, which can be really important to developing methodological standards. So, because many of these challenges are really spanning disciplines, I think it's going to require close collaboration between climatologists, epidemiologists, social scientists, data scientists to really bring in that perspective of what are the uncertainties inherent in different data sources. Right now, we're just talking about the exposure side. The health outcome side also has its own sort of set of uncertainties and biases that climate scientists, for example, might need to be aware of if they were getting into this space. And then finally, for the broader systems level, partnerships across agencies and professional societies, trying to harmonize exposure definitions and improve interoperability across organizations like NIH, CDC, NOAA, NSF, investment in high quality data sharing platforms and environmental monitoring infrastructure is going to be essential to creating shared access to high quality meteorological data sources. And then engagement and validation of communities and data collection systems. So it's really important to start thinking about how we can validate data that comes directly from community participants, especially for things like rainfall that have really significant small scale heterogeneity that we won't be able to sort of have at sort of a national top down level. So kind of in closing, I think the selection of our exposure in extreme weather and health research is not just a technical detail. This is something that requires a lot of thought and consideration as we move forward in this, because it really is going to shape the mechanisms that we're capturing in our analyses, the causal inferences that we're making, and ultimately will influence the interventions that we develop and the public health decisions that we're making. Okay, so just in conclusion, I want to say thank you to all of the investigators on our SCORCH team. We have a nice interdisciplinary group that works on this. And of course, we want to acknowledge that this work is supported by NIEHS for our P20 Center and really appreciate that support. So looking forward to the conversation.
Awesome. Thank you so much for that. Great talk. Really inspiring work that you guys are both doing. So thanks so much. I want to remind everyone in attendance that you can ask your question a couple different ways. You can raise your hand and we would be happy to have you unmute and ask your question verbally. You can also enter questions into the Q&A and we will pose them to the group here. So I'll kick it off with a question or two while folks are organizing their thoughts around what they want to ask. So I thought that simulation that you presented, Melissa, was super interesting. And I was just wondering, are you working on a publication to help kind of disseminate that to this audience and others?
Yeah, so the project or the investigation that sort of sparked that simulation is currently under review. And so that's a preconception and prenatal exposure to heat waves in associations with APGAR scores. So we use a lot of the lessons from that in there. But the simulation, I hadn't actually planned on submitting it until a couple of weeks ago. And so we're just finalizing like a couple more parts of the simulation just to look into it a little bit more thoroughly, and then hopefully we'll submit it within the next month. I realized during the course of this that actually writing a paper on a simulation and not real data is way easier. So
there's probably a couple of ways to get that out there, but it just seems like really valuable in terms of methodological development to kind of just have that type of study out there and spark a conversation around it. So yeah, I'm glad to hear that we can look forward to seeing that sometime soon, sounds like.
Yeah, hopefully.
Okay, so again, really welcome folks to enter their questions in the chat or raise their hand. But in the meantime, let me ask a couple more questions. So Kacey, at the end, you were kind of talking about some things that you think either that could happen kind of at the cross-institutional or cross-agency level to kind of start to come around to some standards to use for, studies of extreme weather and definitions. And so I saw that you had some great suggestions that I think we at NIH and, our Q program could learn from, like kind of organizing gatherings to get the right people in the room to discuss these topics and kind of get some products out there. But I was just curious, what ways have you thought about that, maybe besides that could help kind of get us moving down a path towards more standardization and harmonization. So like if the community were able to come together and kind of think of some ways to kind of make recommendations for how to move forward, like what would be the next step, like how can we get everyone moving on the same path on this?
Yeah, I think it's a challenge. I think even in sort of things that are more operationalized with lab standards, et cetera, it is still tough to get people on the same page. I think the first step is just to acknowledge that there are these challenges. I think a lot of people talk about them, but we haven't really had an organized conversation about it, or at least we haven't had enough organized conversations about it. I think extreme heat community has probably made the most progress. I think we could learn a lot from what has been developed in extreme heat and try to translate that into sort of flooding exposures, wildfire exposures, et cetera, and sort of keep that conversation moving. I think some of the things that could be useful is to have a best practices document, right? I mean, I think that it has to be tiered, it has to be flexible. As I mentioned, there's, if you're conducting a study where there's just, very limited meteorological data, that doesn't mean you don't want to conduct a study there. It just means you have to couch it with that uncertainty and really approach it in a sort of thoughtful way. So I guess I don't have a perfect answer for like, okay, this is what we have to do, but yeah, I think those are some thoughts on what to get started.
That's great. Yeah, that's great. And maybe I'll leverage this question that's in the Q&A right now, which is, the work that you showed, at least for the heat today, was kind of focused on the United States and thinking about, our climate conditions and the data that we have available to us here. But what about, internationally? Obviously, these issues are global issues. Do you have any insight into kind of lessons from international settings that might help inform this work or complicate it?
Yeah, I mean, the data access and the data sources are just not evenly distributed, right? So one of my collaborators at the World Meteorological Association was talking about how they talk about this a lot, how there are data deserts in parts of the world that need to be filled with just more networks. There is a large push to try to improve that infrastructure to collect good meteorological data. But you think about places that maybe have a lot of topographical sort of variability, and they may have a smaller network of meteorological stations. But are there ways that we can pair the data that they have and then do some spatial interpolation based upon the characteristics? I think there's a lot of things that they do in the climate world to make products that are cohesive and valid, that I, as a health researcher, am not as well versed on, that we can really sort of improve on as we sort of adapt what we're doing in the health world.
Yeah, that makes a lot of sense. Lauren, it looks like your hand is raised. Would you like to unmute and ask your question?
Sure. One quick thing with the chat, I can't enter anything into the chat or see anything in the chat. So I don't know if other people are having that issue as well. But
Lauren, are you able to see the Q&A? So the chat is disabled, but do you see that like next to it, there's a Q&A?
No, maybe not on I don't know, maybe not on my
all right
version.
But why don't you go ahead and ask your question verbally? Yeah, thanks for that.
Yeah. So in terms of submitting like applications or proposals to NIH or NIEHS, is there any current guidance on like how to frame the kinds of like either flooding or heat exposures if like we wanted to measure that within a study?
So in terms of
not for Ashley.
I can jump in for NIH, but I'm going to turn it back to you guys in a second. So, I mean, for applications, no, right? We don't specify anything in particular about how these exposures should be measured. that said, when an application goes to study section, we do hope that, the accurate experts are in the room who would be able to assess whether what's being proposed makes sense in terms of what would be most appropriate scientifically. And I think it's that kind of like, what is most appropriate scientifically question that we're talking about, kind of trying to get a little bit more consensus around. So I don't know if that's helpful to answer your question, but turning it back over to Kacey and Melissa, I think you guys just in this talk alone, you kind of gave some suggested guidelines for, in this particular type of situation, I would recommend, using a binary, like a absolute threshold rather than a percentile based one or something. But are there any other kind of broad recommendations you think you'd make at this time, or is that what we kind of need to, as a scientific community, get consensus around?
Yeah, I mean, I think that's what we're trying to move towards, right? I don't think there are specific sort of standards out there where, this exposure needs to be measured exactly this way. And I don't know if we actually should go to that strict of a standard, because there is so much heterogeneity just in how these health effects are manifested after extreme weather exposure. But I think that there are standards, not necessarily standardization, if that makes sense. So I would say that when you're putting in an application or writing a manuscript, that you try to think about, like, why did you select that particular definition? How is it meaningful to the biology of your research question? Why did you use those lags that you use? So make sure that you're sort of justifying your choices and you don't just sort of pick mean temperature on a weekly basis without really thinking through what does that actually mean in relation to the development of the health outcome.
Yeah, and as a study section reviewer, I would never punish somebody just for saying they wanted to use percentiles. I think that, or any other, type of exposure measurement model. But I do think, like Kacey said, it would just be important to think about how that particular exposure measurement is, is appropriate for whatever it is you're trying to study and your setting. So I think we just need to think a little bit more deeply about how these things can affect our bias and exposure misclassification.
I'm going to try to get to some of the questions that folks have entered into the Q&A now. How about this one from Talia? No doubt that exposure choice matters, but when thinking about warm versus cool cities using percentiles as exposure in the simulation, are we not just seeing effect modification by warm versus cool city, indicating that a relationship might be present in warm cities, but not in cool cities, because the 95th percentile temperature is much hotter in warm than cool cities?
Sorry, I'm having,
Can you guys see the questions?
I'm having trouble operating Kacey's computer, but so we didn't actually. So the question of whether or not there's effect modification is different, right, from what we were modeling. Because I didn't explicitly model an effect modification. I said anybody who's exposed at an absolute temperature greater than 85 degrees experiences increasing risk as the temperature increases. And so if somebody in a cool city is experiencing those high temperatures, then they also would have increased risk. It's just that when you define the risk by percentiles versus by absolute temperatures, you're just getting a lot more exposure misclassification. So one of the things I'm doing in the paper that I didn't present here is looking to see what happens when we exclude cool cities, or do the effect modification just look at the effect within each city, but the effect should be stable across different kinds of cities. So like in the real world, we might be seeing effect modification because of city level adaptation to heat, right? Like housing structures, support for cooling systems, shade. But when we're just looking at the association between ambient heat and a health outcome, for this particular simulation, there's no effect modification built in. Does that make sense?
I think it makes sense to me. So hopefully also to the person who asked the question. There's another kind of related methodological question. Do you think it matters whether heat is the main exposure of interest or a confounder when you're choosing your heat metric or defining thresholds? I know that also wasn't something explicitly covered in your simulation because you were looking at direct effects of heat rather than confounding by heat. But I think the question is just, if your exposure of interest is something else and you want to include heat as a confounder, would your choice of heat metric be equally sensitive to the sorts of things that you discussed today?
Oh, so I don't think we can extrapolate to that situation. Like if you're thinking about like the association, for instance, like between ozone and an outcome, and you want to look at controlling for heat, I don't think we can. Maybe we can, but I haven't thought about that. So I don't want to say that we can extrapolate to that situation. And
But
then
it
for
seems like it'd be worthwhile to explore possibly
yeah,
how it might affect the result, right?
well, definitely for people who are interested in air pollution, I think if they want to control for heat, it would be important to control. But things are different as a confounder than as a main exposure. So then for studies in the Midwest, which heat metric do I think works best? I mean, so I think if you have a bunch of fairly homogeneous cities, then your percentile-based estimates should be fine. But then your absolute temperatures would also be fine. I would say just think about like what are the signals for the true biological heat effects, and then try to model it as closely as possible. And then probably in the Midwest, heat index and humidity would be a lot more important also to include.
Okay, we might have time for maybe just one more question. I'm scanning here to see. So there's a question about using outdoor temperature. Often we use outdoor temperature as a metric, right? Because it's available, but it might not reflect true exposure. You touched on this a little bit. I think this comment is talking about people staying in the shade, not exercising, or staying indoors with air conditioning, for example. Can you comment on misclassification on true exposure due to heat waves that could actually change people's behavior? So heat changing people's behavior that therefore changes their exposure, I think is the question.
Yeah, absolutely. And that's sort of what I was trying to get at that one of those initial slides where I'm like, okay, you have your meteorological event and then you have your health outcome, and then there's like all of these different things that can mediate that effect, and you have sort of effect modification that's happening. But I think, people, so there are factors that will influence whether or not you're actually exposed, even if it's hot outside. And so that's why it is more recognized that we need to do things like have people wear eye buttons or have some sort of validation of their personal exposure. This could be done through many different strategies. It could be through surveys to assess sort of daily heat exposure. It could be through these wearables where you're actually getting individual level exposure. So maybe even if it's just on a subset of your participants, to be able to get some validation that, yeah, we're actually kind of in the ballpark. But in reality, you're not going to be able to have that for every study that gets done, right? It's expensive, it's time intensive, and we have a lot of really rich data sources that are already available that we should be using to try to explore these questions, which I think is why we need to have a gamut of studies before we declare that something is, you have to have that compendium of evidence to really sort of state causal association. So you need to have studies kind of across that spectrum. And I'll let Melissa sort of close out on that.
Yeah, so the closer you get, the more proximal you are to your outcome, which would be like personal heat. Theoretically, the better your exposure misclassification gets, and also the stronger your effect estimates are going to get. But ambient heat, we have to think about it as sort of an instrumental variable that's affecting personal heat, right? So it's a little bit less biased by confounding. So like the ability to access some of these cooling structures or air conditioning or body regulation. And it's because it's more distal, you get more exposure misclassification for personal heat, but you get slightly better properties from using something that is an instrumental variable. So that's the advantage of using ambient heat, although you give up the exposure, the better exposure classification from having personal heat measures.
We're a little over time. I want to thank you guys both so much for being with us today, and thanks everyone for attending. Really interesting talk, and I hope everyone has a great rest of your Friday and weekend.